This is 5 or 2 from the left.
Okay, how about cosine of pi over 2? We had to go from the left on that one because for tangent, it would be undefined. The limit wouldn't exist if I said the limit at pi over 2. You can't do it because one does this, all right? So I had to say from the left. That's defined. The cosine doesn't care because it's defined from the left, it's defined from the right, so therefore it's defined in both of them. It goes both. In each case, cosine of pi over 2 is what? 0. Good. So this is infinity to the 0. Is it one of the indeterminate forms that we can work with?
Yes.
Look over there. Is it one of the indeterminate forms that we can work with? Yeah. Now, here's the idea. If I didn't mention it before, here's the idea. We are always trying to get this down to the form of 0 over 0 or infinity over infinity. Nudge if you understand that concept. We can't do anything with this right now. We can't do anything with that. So we're going to work with it. We're going to use probably this technique. That's why I said try this for each of these cases. Try doing this. It'll help you. Because if you can do this, if you can rewrite it as infinity over infinity or 0 over 0, then we can do a L'Hopital's rule. So we're always trying to work with these things to get them down to an indeterminate form, which we can work with. So changing this type of form into 0 over 0 or infinity over infinity. Okay, now that we have the idea, tell me the next step. Please, what would you want to do? Okay, let's all do that. You know what? You could even do it right now if you get the hang of it. You could write e to the limit cosine x ln tan x. You guys see that? That's what we're going to get ultimately. I'm going to show you the steps, but you could do it right now. That's what I would do if it was my paper. I'd write e to the limit cosine x ln tan x. So E ln tan x cosine x. The two things we're going to do, which is why I said this earlier, if you get in the pattern of this, because you're going to do it a lot, okay? Yeah, this moves down all the time, doesn't it? That exponent moves down all the time. This E comes out all the time. So we end up getting E outside of our limit to the limit. X approaches pi over 2 from the left. Cosine x times ln tan x. You know what? Every step that you do, you got to check what type of form you're working with now. So let's see if this works. Okay, always be checking to see if it works. Pi over 2. Let's do this. How much is that? 0. It's not going to change what's happening, right? We just want to check the form to see what we can and can't move. So that's 0. How much is that? That's infinity. Ln of infinity is still infinity. Which one would, well, I'm sorry, I should ask you this. What should we do now?
Move one of them to the bottom.
Move one of them to the bottom. Okay. Which one are we going to move to the bottom? The ln or the other one? Yeah, it's rarely the ln because if you imagine this from over here, if I move this to the denominator, I get 1 over ln x. You with me?
Mm-hmm.
That's really hard to do. 1 over ln x would take the derivative of 1 over ln x. That's going to get a little difficult, okay? We'd have a chain rule. We'd have ln x to the -1. We bring the -1, you have -2, and then we have a chain rule after that.
But it's possible.
It won't work out for you. It's possible to do. You can do the derivative of 1 over ln x, but it's not going to work out like this. Okie dokie. So I'm just going to give you the hint here. You're rarely, if ever, going to put this one on the denominator because you're going to get lots of chain rules that way. Does that make sense to you? This one is the one we're going to move down. We might get chain rule, we might not, but that one's going to be easier than the ln in most cases. So we still have the e. We still have a limit pi over 2 from the left. We got ln. We got tan x. We got 1 over cosine x. You guys okay with that so far? So you can do that every time. You say, hey, cosine x, no, let's just put it over 1 over cosine x. It's the same idea. Now, of course, we can simplify this a little bit. Maybe we don't want to work with 1 over cosine x. We might want to work with 1 over cosine x is what? 0. Let's call it secant. Okay, now that we've done that, now that we've done one more step, let's check to see what type of a form we have. Hopefully, this process, it should work for you guys. It should make it a 0 over 0 or an infinity over infinity. Let's see. Now, this shouldn't have changed from here. This should be the same. So when I plug in pi over 2, tan from the left, tan x is still infinity, correct? That means ln of infinity is still this is still infinity. Secant x, as x approaches pi over 2. Remember that this is 1 over cosine. How much is cosine? Remember it was this. How much is cosine of pi over 2? 1 over 0? Infinity. So this is infinity over some form of infinity. Can we do L'Hopital's rule right now?
Yes.
Then do it. Hey, what are you going to have to do for your derivative of ln tan x? What is that? 90% of the time, it's correct answer. That's right. Yay. Let's see if you knew what you were doing here. Ladies and gentlemen, the derivative of, remember, this is not, thank goodness, this is not a quotient rule. What's the derivative of this guy? Secant x squared tan x. Here, how we do derivative of ln is 1 over the inside times derivative of inside. So we have 1 over inside, here's 1 over inside. Got it?
Yeah.
Times derivative of inside. What's the derivative of tan x? So we have secant squared x over tangent x. Show of hands feel okay with that so far. 1 over inside, that's where we get the tan x from the denominator, times derivative of inside, that's our secant squared. What do you think we should do now?
Check to see if it's still 0, 0.
Should we check it or should we simplify it? Yeah, you gotta simplify it first. Before you start checking again and again, let's simplify it. So can you simplify that?
Yeah. And secant.
Take a little side road here. So we have secant squared x over tan x, right? Times, if you put this over 1, if you put that over 1, division is the same as multiplication of the reciprocal. So we would multiply by, what's going to be on the numerator?
1.
Cool, all right. Let's do it. What's going to happen?
Secant 1, secant.
Gone, almost gone. So we'll have secant x over tan squared x. You guys okay with that one?
Yeah.
Now here's an issue. If you try to do the secant x, that is going to give you infinity, isn't it? This is going to give you infinity. You probably could do another L'Hopital's if you wanted. However, sometimes it's worth your while. Isn't that infinity also?
Yeah.
Infinity squared is still infinity, right? So it's worth your while to simplify as much as you can. So what I'm seeing here is that if I write this just a little bit different, if I write this as secant x, look at tan squared x is the same thing as cotangent squared, 1 over tan squared x, same thing as cotangent squared x. Are you with me on that one? We just some identities here. Well, what I'm seeing out of that one is that I could do 1 over cosine x times cosine squared x over sine squared x. This is our secant. You guys follow me on that one? This is cotangent squared. You follow me on that one? You with me still?
Yeah.
Can you simplify that?
Yeah.
Yeah, why not? Let's do it. Cosine squared. So yeah, we did a lot of trig in this one. I want to make sure that you guys are okay before I go on. You okay that this is definitely true?
Yeah.
And this is true?
Yep.
And this is the same thing as 1 over cosine? Hey, this same thing is, remember, if tangent is sine over cosine, cotangent is cosine over sine. So we have that. Simplify it. Now, let's just pretend we have a limit out front. If I do cosine of pi over 2, how much is cosine of pi over 2 again?
0.
How much is sine of pi over 2 again?
1.
I have 0 over 1. Is it okay to have 0 over 1?
Yeah.
Then we've just evaluated our limit without having to do another L'Hopital's rule. Does that make sense? We kind of avoid this whole secant tangent thing and then 2 tangent secant squared. That's ugly. So make it easy by simplifying as much as you can. Not just once, as much as you can. That a lot of times makes your problem that much easier. Did you guys understand the concept here? Yes, you probably could do another L'Hopital. Should you? Probably not. Probably simplify as much as you can. So let's wrap this thing up. We've got and e. We've got a limit. We got x approaching pi over 2 from the left. And now we have, well, the only thing that we did, here's our star. We did our star. And now we have cosine x over sine squared x. Okay, let's do it one more time. You guys okay with going from here to here, yeah? What was cosine as we approach x equals pi? 0 over
1.
So this would be e to the,
0.
of course I said, no, it's not always 1, and then I gave you an example that was 1 again, but just a coincidence, okay? So we get e to the 0 again, we get 1. Show of hands feel okay with that one. That's a tough problem, it's tricky, that's a lot of stuff in that problem. Look at all the steps we have in that. Would you like to try one more?
Yes.
Okay. Ideas don't change though. Ideas are, if you have an indeterminate form, try to work with it, make it 0 over 0 or infinity over infinity, and then you do L'Hopital's rule. After you do L'Hopital's rule, you simplify it every time. After you simplify, you check it again. And if you still have L'Hopital's rule, cool. If you don't, then you evaluate your limit. That's the whole idea. Okay. This one's gonna take us a while too. Okay, now you really need to tell me what to do, okay? What would you do first? Try. Right, good. Let's do it. Let's plug in infinity and see what we get. What's 1 over infinity?
0.
What's 1 minus 0?
1.
And what's that go to?
Infinity.
So this is 1 to the infinity. Is that one of those indeterminate forms that I gave you in that sheet?
Yeah.
So if it's that one, what should we try? The e to the ln thing. Why don't you do that? Go ahead and do the e to the ln thing. Notice I'm going to give you the shortcut right now. Of course, you can write this out and then write this out, but I'm going to do it in one step here. When you get the hang of this, this is absolutely fine. Just don't forget, oh my goodness, don't forget about the e. Okay, don't forget that e, it's important. So what I know is that I could write this as e to the ln of this argument. Well, that's the same thing as pulling out the e, having the same old limit, having the x come down because I have an ln of the inside. Okay, you need to make sure these are okay. I'm going from here to here. Do you guys see that I'm basically doing the same thing, only in one step? Show of hands if you're okay with that one. Okay, that's everybody. That's good. So same idea. It's still e to the ln, isn't it? And this is still an exponent, but I'm bringing it down. Okay, now let's check it again. Nothing really should change. I should have a 1 up there somewhere, and I should have an infinity. That's still infinity. Now this thing, let's look at that. That's going to change a little bit. Look what happens here. Here's an infinity. When I plug in infinity here, what do we do?
0.
1 minus 0?
1. 1 minus.
How about ln of 1?
0.
Oh, so I have infinity times 0. Oh, that's one of those indeterminate forms that I can actually work with. Isn't that kind of cool? When we do the ln, it changes from that that 1 to that infinity. That's cool. So, I'm sorry, to the 0. I misspoke. Which one would we want to move here, the ln or the x? Let's do that. So go ahead and do that. How do I move it? Do I just move the x to the denominator? What do I do? Okay, yeah, that's the way that we can do that.
Can you also say x to the negative 1? Or would it be?
Yeah, you can. I do that one because it's easy for me to see the limit of that. Sometimes I see x to negative 1, I go, oh, it's hard for me to think. I could do that again. But you can. Yeah, you can do that. So let's make sure that we actually have an indeterminate form. We already figured out that this one's 0. Let's look at this one. Remember, the 0 came from here. Oh, yeah, that's infinity times 0. So if I move an infinity to a denominator, the infinity changes from infinity to another
0.
a 0. Now I got 0 over. Do you guys see the 0 over 0?
Yeah.
This is 0. It's 1. ln of 1 is 0 over 0. Hey, what can I do every time I get 0 over 0? Why don't you go ahead and work on the L'Hopital's? This is going to be a little interesting, okay? A lot of stuff going on here. The denominator, fairly straightforward. We actually already did that one in one of the previous examples. So when I have 1 over x, of course, that's really x to the negative 1, as he said. Bring down the negative 1, subtract 1 from it, put over the negative 1 over the denominator of x squared. You guys okay with the negative 1 over x squared?
Yes.
Have you guys finished this one?
Yes.
Okay, so derivative of ln says, hey, 1 over the inside, where you're not changing anything. No problem. 1 over the inside times the derivative of the, now let's look at the derivative of the inside. The derivative of 1 minus 1 over, I haven't done this in a while, but it's kind of nice. So 1 over the inside times derivative of inside. I want you to see what happens here. So e. Limit x approaches infinity. We've got negative 1 over x squared. We've got 1 over 1 minus 1 over x. Times What's the derivative of 1? What's the derivative of 1 over x? So if I have minus a negative, that's going to become, so if this whole thing gives us 1 over x squared, hopefully you understand why. Same reason this gives you negative 1 over x squared, we have minus a negative. So basically it's 0 minus negative, like that. That's really the derivative. Derivative of 1 is 0. Minus, minus. Derivative of this thing, hey, it's the same. It's negative 1 over x squared. Show of hands feel okay with that one. So what they give us in the long run is positive, positive 1 over x squared. Okay, cool. Now,
They simplify
probably simplify it. I'd probably deal with this maybe. Do y'all see that that's going to distribute across that denominator? So we'll get big fraction 1 over, looks like we get x squared minus x. X squared, there are other ways to do this, by the way. I'm just showing you one. So x squared minus x, this is negative 1 over x squared. All right. That looks a little better, at least. We have fraction over fraction. We know that when we have a complex fraction like this, instead of having the division, we can always multiply by the reciprocal of the denominator. All right, well, that's e. Man, just some algebra now. 1 over, tell you what I'm going to do. What am I going to do with that?
Distribute the factor out the x.
I'm going to factor x, that's right. X times x minus 1. And I'm going to have negative x squared over 1. Division is the same thing as multiplication by the reciprocal. So I'm going to reciprocate. Now I'm going to simplify. What simplifies here?
The x. One of the x. And then the squared ones.
Okay, so this thing's completely gone. This thing's almost gone. And let's rewrite it. Let's see what we got. Remember, the idea is do L'Hopital's rule, simplify it, rewrite it, and then reevaluate. What's on our numerator?
Oh, x.
Close, negative x. Denominator, I've got x. Okay, check it out. We're going to reevaluate right now. So take our infinity, plug it back in. This is what we do every time, right? Every single time we reevaluate. Hey, what's negative x as x approaches infinity? This is negative infinity, that's right. What's this as x approaches infinity? Okay, what's infinity minus 1? Like the little kids. I'm better than you by infinity. I'm better than you by infinity plus 1. Okay, that's still infinity. That counts. It's an infinity over an infinity. What are you going to do now? And that should answer your question. Can you do it more than once? Of course you can. Anytime you have, listen, just because it has an e on it, it doesn't matter. It's still a limit, right? It still falls into the whole idea of if it's infinity over infinity, do a L'Hopital's with it. So we've got e to the limit of x approaching infinity. Everybody, derivative, oh, this is so nice. Goodness gracious. How much is that? Over 1.
Negative 1.
So this is going to equal e to the negative 1, or
0.
1 over e.
Times 0. Oh.
So when we get our final answer, you want it to be in the notation of the limit of the next approaches whatever, and then the answer.
This is literally exactly what you have every single step. This is what you should have. So you should have writing it as e with your function of x moving forward, then ln. You should be showing me all this work. You should be showing me this stuff, our simplification, getting down to here. Then you go, okay, this right here, this is still, you write a limit. Because when you do the L'Hopital's rule, that's your resultant of that. This is your derivative. It is negative 1. The derivative of this is 1. And then you go, well, hey, a limit of a constant is the constant, so no big deal. It just happens to be that limit of negative 1 is negative 1. E to the negative 1, just want to read. That's it. Should you feel okay with that? Does it make sense, this whole idea? That's kind of a tough one, right? There's a lot going on that problem. But do you have any questions at all? Question?
On the second arrow right here, can you just like 1 over x squared over the 1 over x? Can you just cross like cancel those both out because they're products of each other?
These ones?
Yeah.
Yeah, you could do that. So I said there's a couple different ways that you can actually do this. That would work out, I think, the same. Actually, it might be even a little bit better. Because if you did this, multiplied by the reciprocal, these are gone. This thing right here, this becomes negative. This thing right here is 0, right? 1 minus 0 is 1. You just get -1. So yeah, same thing. I did want to show you this way, that way you understand, because we had a question earlier. Can you do a L'Hopital's rule again even if you have an E? The answer is yes. In this case, you do. In the other case, you wouldn't have to. Just like we had over here. Could you have? Yes. Did we have to? No. So we probably could have made this a little bit easier. Absolutely. But there's multiple ways to do these. My suggestion would be simplify as much as you can. I probably didn't do that here. Probably could have simplified that and made it just a little bit quicker. Be okay with that one?
Yes, sir.
This would be a great time for questions. Are there any other questions at all? So, do you know what I mean by indeterminate forms of limits? Indeterminate forms of limits, what's your goal? What are you trying to get?
0 over 0 or infinity over infinity.
Once you get 0 over 0 or infinity over infinity, what do you use?
L'Hopital's
That's
rule.
right. That makes these limits so much easier than any other way that we have, okay, that L'Hopital's rule. Is L'Hopital's rule a quotient rule?
No.
I didn't spell it. Oh my goodness, that'd be harder. This is just derivative of the numerator over derivative of the denominator. We look at the comparison of the derivatives of the functions rather than the numerator we have, okay? That makes these limits so much easier than any other way that we have, okay, that L'Hopital's rule. Is L'Hopital's rule a quotient rule?
No.
I didn't spell it. Oh my goodness, that'd be harder. This is just derivative of the numerator over derivative of the denominator. We look at the comparison of the derivatives of the functions rather than the comparison of the functions themselves, and limits end up being the same. Last thing, are you okay that we can always do e to the ln of a function and it's still exactly the same? Okay, that's the idea.
Well, we always see it in that form.
Only pay for what you need with Liberty Mutual. I just said that.
The first day of class, filled with possibilities and unknowns. That's why Check Study Pack empowers you.
Okay, so time for a new chapter, time for a new section.
Hast du keinen Zweifel daran, wir schießen immer, dass da sogar ein kleiner Vogel frei über die Mauer fliegen? Hast du keinen Zweifel daran, wir schießen immer, dass da sogar ein kleiner Vogel frei über die Mauer fliegen? Der Thron zu Bildschirm, die Leute erinnern sich an diese Tragödie. Ist das der oder der Tag? Sustaining top on dead mountain in that moon top Disgusted with it, how stiff and spotted and lost gone. Midnight, clouds on concrete, cowboys, lovers, they light, the streets are uncaring, und sneaking, und touching, foundational in his head, taken feeding me there by thoughts again. Even though I can see me, time is levels, clouds Turning beat anywhere by thoughts again. Even though I can see me, time is levels, clouds Every drop beside a dream. Oh, man, please remember me. And on the bus to chase a dream. Underneath the canopy. Standing right, we're flying over the clouds. As the daylight that dies, I stereo breathing. Endless to the chasers, a demon's high tops, waiting for seas of the ground. It's passing down. Standing right, she's breathing out from the ground. Like the smell of my nail, blue stars on this mind, so fast, it is broken, the feeling's spoken, so we just let it rain, is it just time?
YouTube Music has upgraded playlists. Get song suggestions that match your playlist vibe, collaborate with other tastemakers, and discover more music with our ready-made playlists for any moment. Explore YouTube Music today. personal guide to the world of indie music. Get a free trial of YouTube Music Premium today.